continue from whatever I did last time, and that was the discussion of Schmidt decomposition, and I will kind of summarize what I wrote down last time, that you have some quantum system in a joint Hilbert space. One part is A, the other part is B. And I wrote it down as a particular decomposition where the double sum in here for both the parts is reduced to a single sum, but then these two are correlated in a very particular manner, and that correlation is implicit in the choice of what is I and what is I prime. It's not just any arbitrary vector. And how are these vectors defined? They were defined as the eigenvectors corresponding to diagonalization of the reduced density matrix. So this was reduced over A, and corresponding eigenvectors over here, Pi becomes the eigenvalues, and equivalently the reduced matrix of B, the same eigenvalues appear over here, but the eigenvectors of it can be different. So this is the mathematical form of Schmidt decomposition, and of course I should put this variables, that is Pi are probabilities, and they add up to 1. They are just a normalization. Okay. So I gave some consequences of this derivation. The most important feature is the one-to-one correspondence between eigenvectors in A and eigenvectors in B. And of course there is no restriction on the two system sizes, so only certain subset of eigenvectors will have non-zero eigenvalues, other will have all zero eigenvalues. And I wrote down several points last time. I think I wrote down 4. So I will start with number 5. That is something which is a characterization of these eigenvalues. Of course, if you are given the whole set of eigenvalues, you give the full description, etc., and you know everything. But is there any what you call more compact description of these eigenvalues which will give you some important feature of the correlations or the system? And the answer is that yes, this is something which is well known in statistical mechanics, that if you are given some distributions of probabilities, you can calculate various quantities, for example, you can calculate the average, you can calculate the moments, and you can calculate even more complicated function. So the function which is useful in many of the analysis of the properties of this system is something which computer scientists call information and the physicists call entropy. And what is that function? Well, it can be written in a rather simple form. It's a function of the set of the whole probability distribution, but it is just one number. So of course it doesn't have all the information which is there in the distribution. It is one number which gives some property of that distribution, and it's defined as pi log pi summed over all the values of I. Now again there is a choice of convention. In physics, what is used is a natural logarithm and with a proportionality constant, which is called Boltzmann constant, because Boltzmann was the one who wrote down this function for the first time. And mathematicians or the computer scientists use logarithm to the base 2. So it's well known in mathematics that log in one base is proportional to log in another base. So there is some overall proportionality constant. We don't worry too much about it, and depending on the convention, choose it. So in all the applications of computer science, this is typically taken to be log to the base 2, because we deal with systems with binary variables. So log 2 is convenient. So there is another way of writing this in a more compact fashion, that this is just a average value of log pi. How do you calculate average? Take the function and multiply by each probability, and that is what this is. And if you write it this way, it kind of gives the motivation of why Boltzmann took this particular form, and that has to do with our interpretation of probabilities, that if you have two systems which are completely independent, then the joint probability is the product of individual probabilities, which means that if I take one coin and toss it, say up comes with half probability, another coin I toss it, it comes up with half probability. What is the joint probability? That both the coins are coming up top. That probability is half times half is quarter. So the probabilities of independent events multiply. And Boltzmann wanted a function where whatever that function is for independent system, it adds. And the easiest way to convert a product into sum is take the log. So log of x times y is equal to log x plus log y. That's what it is. So this function by design, it's additive for independent systems, and that is of good use. Of course, if there are correlations, the systems are not independent, it will take some other values. So it can be used to quantify correlations between different systems as a function of whatever the PIs there may be. And there is a quantum generalization notice that this can be calculated directly given the Schmidt decomposition. You find this pi and calculate this S of pi, and it can be given a interpretation at that stage itself, which is for pure states. We know what the situation is. One pi is equal to 1, all others are 0. That is the nature of the density matrix for a pure state, and that implies that S of pure states equal to 0. And now look at this reduced density matrix. It will have some distributions of pi, and they are in general mixed states, where S of whatever the set of pi is in general non-zero, because it's not the special case where one of them is 1, but it will be a distribution of some times. And so one can now say how different this reduced state is from a pure state, okay, which is the difference between these two values. So if the difference, which just happens to be this value because one of them happens to be equal to 0, so that it becomes a quantitative measure of how much correlations is present between A and B. And I mentioned last time that this 1-to-1 correspondence, when there are more than one term in the sum, the state is called entangled rather. So this difference is it's a measure of the property which I call entanglement. How much is the correlation between the eigenvectors over here and the eigenvectors over there, depending on the distribution of pi, and it has a name. It is called entanglement of formation. So if you start with a pure state, two parts which are uncorrelated, and by some interaction with part A and part B, they become correlated, which is called entangled. How much is the amount of correlation? Well, this number will give you an idea. And this is a standard label to quantify it, that there is so much correlation present in the system between part A and part B. Yeah.
So the differences between the mixed state as a function. But for pure state, it's 0.
Yeah, because the
Yes. So
value is 0.
essentially, it's just the entropy of the mixed state.
Yeah. But assuming that you are comparing it with the pure state. Yeah. Because pure state has no correlation, this has some correlation. You try to figure out how much is the correlation, then this is a quantitative function which can give you an idea of that. Now, we also want to write this thing down in the quantum language, which means that I want to write it as a function of the density matrix itself instead of the pi. But we know that pi are nothing but the eigenvalues of the density matrix. So there is a straightforward way to extend it. So what is that expression? And well, right now it is equivalence. I can use the same symbol. So suppose I want to convert this into this expression. Okay, and I can take one over there. And it will, by construction, the eigenvalues are the same. So it will be the same function whether you look at part A or part B. What is that function? So I want to write this expression in terms of rho. So the easiest thing for me to do is go to this basis where rho is diagonal, and then the expression for the function of a diagonal matrix will be the same as the expression for the number. You just do it one by one for every element. So that will give you a result which looks like rho log rho. But this is the expression only in the diagonal basis. What will be the more general expression? Well, then you have to ask what happens when I do a unitary transformation. And as I have mentioned before, how do you define a function of a matrix? Well, you somehow or the other write it as a power series, and then you can do whatever you want with it, including applying to a structure of a unitary transformation, because unitary transformation of a power series is the same as the unitary transformation of individual terms done one by one and then added together. Doesn't do anything complicated from the property of a matrices. How you multiply matrices, the unitary transform will just act globally and all the intermediate terms will have the unitary factors which will all cancel out. So it will be in general a unitary transform of this object. And then it will look different, it will not be a number. So how do I construct an object which takes this expression and still produces something which is independent of the unitary transformation? And last time I mentioned one useful function which does that is a trace. So trace remains invariant after a unitary transformation. So yes, I can transform it, but I take trace, so the unitary transform drops out, and then it becomes just equal to this function of the diagonal entries, which is that, and of course there is a negative sign. And since this is valid for either of the two situations, this holds, and this is the expression which was constructed by von Neumann, and well, It has both the labels which I mentioned over here, depending on the context. Physics it is called entropy, mathematics is called information. So remember, you can define this for any arbitrary density matrix. You can look at it in different ways, but one way is just what I explained. You go to a basis in which the matrix becomes diagonal, calculate the function, and then apply the unitary transformation. Unitary transformation drops out because of the trace, and you have a value. And this quantity also is heavily used in many other contexts, not just these bipartite systems. You can talk about those things in more general, maybe in some other application. Right now, this is enough.
S of rho A is equal to S of rho B, always.
They are the same PI.
Yes. They are different. They look different. They are not different.
This is a function only of PI. And it, again, you can go back to what happened for pure state. Pure state, the density matrix will be a projection operator with one eigenvalue 1 and 0, and if you calculate this, this value will be equal to 0, and you can then call it that what is this object, you call it again the entanglement of formation for this density matrix or that density matrix. But the point is that you can calculate it on either of the two parts. So even if you have a situation where you know one part, the other part is the rest of the universe, completely unknown, by observing that one part and finding its density matrix, you can calculate this. Without knowing anything of the environment, you can calculate a measure of how much it is correlated. It is correlated with what degrees of freedom that you don't know. I can know IA completely, I have no idea about what IB prime is, but you can still calculate this measure that this is the amount of correlation. Okay. So these are important concepts, and the power of many things comes from the simple fact that there is a one-to-one correlation that keeps on reappearing in a different manner in different places. Okay. So now let me give a simple example, okay, which is just ask what is the correlation of one qubit with another, or as I said, it can be one qubit with the rest of the world, because only 2 degrees of freedom in the rest of the world will be correlated. Qubits don't have any more degrees of freedom. So in particular, I will just restrict myself to the eigenvalues which can be non-zero. There can be lots of zero eigenvalues, and I don't worry about it. So what are these two dimensions I have to worry about? They are just two states, basis states you can choose to be 0 and 1. Nothing more complicated than that. We have seen them before. And then there will be some products of 0 or 1 on one side and something 0 or 1 on the other side. So totally there are only 4 states. There is a particular basis which is used to describe these 4 states and which turns out to be very convenient in lots of different applications, and that basis is called Bell states. It's a orthonormal basis for these 4 states. And I will just write down some notation. Okay, let me just, one of the notation is this. I think this is called 5. So these are the states where the indices are the same on both the components, but I have mixed them together in some combination which creates this entangled or correlated structure. And similar label can be done with the other 2 states. Which involve the 2 eigenstates which are different. Together they cover all the 4 possibilities 0, 0, 1, 1, 0, 1 and 1, 0. So it is a orthogonal basis, and also you can easily calculate the dot products of one of them with the other. They are all zeros. So it is a orthonormal and also complete basis. So what was the purpose of choosing this particular combination? You can go and look back over here, and this will all the probabilities are equal to half. This is coming from this normalization, which is 1 by root 2. And it allows me to calculate this entropy of formation, this particular value, and I will take the binary log. So it is half log half and another half log half for the second eigenvalue. And log of half is -1 in the binary basis. So add up everything and this number is just equal to 1.
Here I goes from 1 to 4.
Yeah, and only 2 values are there. A 2-dimensional systems. And here is another property which is common for this entropy function, which I can write down. You can look at this expression. It is pi log pi. Pi's are all between 0 and 1, and log of a number between 0 and 1 is negative, which is why this negative sign is stuck, so you get a positive number. So each term is positive by itself, and the minimum value is this for pure states. For any other state, there will be only positive numbers coming here. So already you know what the minimum is. You can ask, what is the maximum of this function? It's not too complicated. You can take a derivative with respect to pi and maximize it. It's not too complicated, but there is a general result that S of pi is maximum when all pi are equal. Prove it by just taking derivative of this. It's not too complicated. And what is that value? Well, I will put the explicit numbers. All of them are equal. So if I have a d-dimensional system, each one is 1 over the dimension. Nothing more complicated than that. So I will write this is minus 1 over d log d. All of these are equal. Sum over 1 over d in a d dimension is 1, and so this number is just equal to there is a plus sign because of I put d and not 1 over d. So this is equal to log of d. This is a generic result, and in the context of statistical mechanics, such a distribution where all the probabilities are equal is well known. It is called the microcanonical distribution in thermodynamics. So, it's a distribution where all possibilities are equally likely. Then it is heavily used in both in statistical mechanics and thermodynamics. It's in some sense unbiased. Everything is equally probable. So that is the situation in general. And if you look at this thing, it just turns out to be a special case of this situation, where dimension is equal to 2. This is the largest entropy. So Bell states, in addition to that, they have largest correlations and so we can go from one extreme to another. Pure states have 0, and this state is the other end of the story. Whatever correlations are the maximum, and sometime in this label, these things are called maximally entangled states. So now one can use this particular property in many different ways. What can be done with so-called maximally entangled states? And that becomes obvious if you stare at this structure, that suppose I know the behavior in one part, the behavior of the other part is completely predicted. That is a consequence of, again, one-to-one map. I have some one variable 0 and I know that Bell state. I can measure one part and without hesitation predict what the other part is, provided I know which Bell state I have. And where will this kind of correlation be very helpful? Well, one thing which I can point out, I'm not going to go into that subject in detail, but it is cryptography. What do you want in cryptography? You have a message you want to reproduce at the other side. And that reproduction is what? It is just a one-to-one map. Whatever you have here, it automatically conveyed over there. And so these Bell states are very useful in constructing cryptographic protocols. And that correlation is completely coming from the quantum dynamics. So if I have this state, I can use it for conveying a message, with the advantage that if somebody destroys these correlations, I will know.
Is it related to teleportation?
Yeah, they are all together. You can send some secret message, or you can send a teleportation, one state reproduced at the other end, whatever it is. So both of those things go together. From the practical point of view, is you have to design the hardware to produce these states. Okay, that is the challenge. Can you make it in the lab? If you can make it, then the job will be straightforward. Yeah.
So, like, how we do it is how we can differentiate from other non-dynamics in the time. If we want to do it, to ask me a question and I will go there, it's makes me that.
Yeah, so everything depends on the correlations. If I destroy the correlation, then I will go back to this pure state kind of system. It's factorized, no entanglement is left. And by measuring any quantity like this, I can tell whether the correlation is there or it's not there.
From entropy,
Yeah. So you have to do some what you call initial work to set up the system, but you can check. If the correlation is not there, this will have some value basically close to 0. When the correlation is present, this will have large value close to 1. And since this is defined only on one of the half the system, I can make checks on one half without worrying about what is happening at the other half. And that is the advantage. So this is one story, and there is another feature which you can also use, that there are only 2 degrees of freedom. So S of, I can write it explicitly, is if one probability is P, the other one is 1 minus P. No problem with that. And then it is a function of a single variable. Whatever one probability of one particular component that I have, and you can ask, what does this function look like? Okay. So the property is that this is monotonic. In for P between 0 and half, the other half is just a copy because P and 1 I see that interchange. And if you plot it, it looks like this. And the monotonic behavior gives you an extra feature that I can tell whether the correlation for one value of P is more or less compared to the other. That's the property of any monotonic function. You can just have to see that where am I? Well, you are given this value, you can predict the other one uniquely. So it allows to order in I can say that this state is less correlated, that state is more correlated, because I have a function which orders them accordingly. And this is another useful feature to know. And well, things are kind of trivial for because the 2 dimension you don't have anything more possible and you can see it explicitly. But this kind of descriptions are used in defining many properties of correlations and entanglement. You can say whether it is more entangled, less entangled, etc. You have a quantitative way of describing it. Now I can point out something more which will be extended explicitly in later lectures about describing the evaluation of a quantum system even when you have only observation on one part, which is just this reduced density matrix. How will the reduced density matrix evolve? Okay. And that can be specified in a kind of a non-trivial way using this idea of Schmidt decomposition. And let me just illustrate it diagrammatically. That suppose I have some reduced density matrix at time 0. What happened? Closing the door or? What I can do using this property of Schmidt decomposition, that I can go from here to the larger space by putting some dummy indices on the rest of the universe. I described that in the previous lecture. I can always do that. So you go to some generic system. It doesn't matter what these dummy states are, I can always do it. That is what counts. And now we know how to evolve this, because that was one of the axioms of quantum mechanics. If I have a vector in a Hilbert space, I can evolve it according to the Schrodinger equation or a unitary transformation. So evolve with some Hamiltonian. Okay. And after doing that job, I will take this partial trace. So this was index A. And I will get the reduced density matrix at time t. So I have now a scheme. This one is a kind of roundabout way to figure out, if I start with some reduced density matrix at time 0, what will be the reduced density matrix at time t. And the question is, can I find a direct equation? It will not be Schrodinger's equation. It will be some generalization. But you can work out it using mathematical transformations which I have constructed just by doing this jugglery. But the final result can be expressed in a relatively simple manner. And there is a name for it. Which I will have to expand. So this label is called completely positive trace preserving map. This is just an acronym, CPTP. Why all those things? Well, trace preserving is buried in the density matrix property itself, that the trace of the row is equal to 1. It's not going to change. And completely positive is connected to the fact that the eigenvalues of this are positive between 0 and 1, and so will be the eigenvalues of this. But there are other names for the same object, and I will write them down as well. One of them is called a quantum channel. Because this is essentially something which will happen when you are transmitting data from one place to another. All kind of other interactions with the rest of the world can come in. It will modify the system in some way, and that will be described by the usage of the word quantum channel. So we are talking about this thing not as a time evolution but as a communication task. It is more commonly referred to as a quantum channel, but it's the same thing. And these labels are too long, so there is a shorter version which is just called superoperator. So here whatever was happening was a unitary operator. What is happening here is a superoperator. But everything which is buried in all these definitions, that these objects are all linear transformation by construction. That was a property of all these things. When you extend it, it's a linear transformation. When you evolve it, it's a linear transformation. When you reduce it, it is still a linear transformation. So whatever combination you end up with, it is still going to be a linear transformation. Linear transformation on the density matrix. And that turns out to be useful. You can actually construct this thing explicitly, which I will do in the next lecture. But it has nice features which you can kind of remember without going into too much elaboration. And it's a going back to the axioms which I wrote down for quantum mechanics. In the Hilbert space, the states were all described as a unit vector without the phase, which was called rays. Here, everything is a density matrix. They are not rays. Rather, they cannot even be described always in the vector language. They have to be matrices. The evolution is always dealing with unitary transformation, but once you find out what the CPTP map is, it is not going to be a unitary transformation. And the third thing is this. The measurements in the Hilbert space language, we are talking about projections, not here. They will also be something else. This? Yeah.
This is pure state, right?
Yeah.
And this CPTP may also be called as a dynamic mapping.
You can find out by doing these things in sequence, and we'll figure it out what that it will look like. But it's something which takes you the system from time 0 to some time t. What?
Dynamic mapping.
Yeah, it can write it as a differential equation if you want. I just wrote it in the discrete form, but because that is more common generically when you have a pure state, the psi abt is some unitary operator acting on psi ab. That's easier to write down. But if you want to go back to the differential equation form, you can write I times d by dt of psi is equal to Hamiltonian acting on psi. You can construct this also in a differential form from there by rather the standard procedure of calculus. Make this 0 to dt, expand in a Taylor series, take the derivative, and you will have a differential equation. But as I have said before, the discrete version is more powerful than the differential equation. It is true for pure states and it is true for mixed state as well. Okay. So this is an important feature, and this superoperator business actually has many applications, and I will go through them sort of one by one. Okay. And again, there will be various consequences based on that, which will kind of follow. But one thing you should remember, that when I did this extension, I just put in some states for B and didn't bother about it. But the point is that I should have this extra Hilbert space available where I can define this vector IB. Okay, it was not there, then this extension would fail. And there is a label which is connected with that feature that is buried in this name. So what is the meaning of complete that any extension should be available. Because I am not specifying anything about this. Depending on what is happening in HA, it will be something in the second half, some correlated stuff. But to guarantee that that is always allowed, any extension should be possible, and every one of those extensions should remain positive, because it should produce a density matrix. So this is a stronger requirement, saying that just some extension is available, that is not enough. Any possible extension should be available. And the proofs which will come will depend on this particular property. We will see where it has to be inserted, that you can do such a thing, but that is a necessary feature. People have tried giving up on this, that if I have some extension which is positive, it is enough, and that doesn't do the job. Okay? And this is a stronger requirement which is used in the derivations, and then everything goes through in the construction, and that has become the kind of accepted formulation. That is why this acronym CPTP is heavily used to describe many kind of phenomena. So now I can give a description which is kind of short, doesn't require too many things, based on all this logic which I have put in place. So the first step is to use the fact that any rho A is a statistical mixture of pure states. Because what was the general situation was, this is a projection operator, it was a pure state. And any general reduced matrix is some probabilitical pi added together. And since everything is going to be linear as far as the density matrix evolution is concerned, I can keep this statistical mixture part outside. I do it for the individual components and then construct the statistical ensemble later with some probability weights. I don't have to worry about that right at the beginning. So this just means that ensemble and mixture both are the equivalent words as far as I am concerned here. And that allows me to simplify the initial state. So to be pure, and the important property is that a pure state is decoupled from its environment. No correlations. So I have just kind of postponed the correlations. There may be lots of different PIs, but I will look at one term, figure out for the individual terms there is no correlation with the environment. I will calculate the evolution, and after finding evolution for all individual terms, I will add them together with probability Pi. That makes the life easy. Okay. So this is a sort of without loss of generality kind of statement. We start from a state which looks like this. Now we do the evolution. We have kind of bypassed this first step, and this IAB0 was simplified to a factorized form. Now I ask what happens under evolution. So it is some unitary operator, because this is a pure state acting on this system, except that this unitary operator may not be factorized. Some combinations of A and B structure together. And choose a complete set of bases, which is something I had denoted as mu b in the previous lecture for this state sitting inside the second Hilbert space B. So whatever happens is can be decomposed in this particular basis. Okay. So what does this now look like? I will just write it. A complete set of bases means that this object is identity. Because set of projection basis, I can put a orthonormal for explicit nature. So this is identity, and I am going to combine it with whatever this thing is. Okay. So I'm not doing anything except that things will be written in a mathematical equivalent form, this identity multiplying by this object. But remember that this mu b acts on the B space, but it also gets involved with the UAB. Nothing is happening to the A part. And that can be now sort of juggled around a little bit, and I will write it as keeping in mind all the contractions which I have to keep track of. So there was this mu b, there is a matrix which had a b part, and then there was a 0b, and that I denote by a new symbol, but that whatever that combination is, it still has this index a sitting over here, so it acts on the psi a. And this mu b, this is the last one, this one is remaining whatever it is. So this is notation, but it is something which is making things look simple. So this is what happened after this particular evolution, and we assumed a kind of nice property which is buried inside this complete orthonormal basis, etc. So property is that if I construct this particular object, it will this is a complex conjugate, and this is state itself, not the state, the inner product itself. And now I can simplify this. What is mu summed over mu b, that was identity. So this goes away. Then there is a u dagger and u, that also goes away. And what I am left with is a dot product of this 0 with itself, and that is nothing but identity. So whatever these objects I cooked up, they are some matrices of dimension of the Hilbert space A, but they have this relation. It is nothing but this completeness identity, that m mu dagger m mu summed over all mu is rather trivial. But now let us go and understand what this will produce in terms of the reduced space. This is just a clever notation, and that means I have to now take the partial trace. This was the definition is just this. How do I write it? It's okay. And now we kind of decompose it, because all which was over here, they were all transformation of pure states. So this is just going to be UAB acting on psi A, and then U dagger acting on the another factor of psi A. One of them is a bra, the other one is a cat. And this can be just rewritten by taking the outer product of whatever is here with itself. And the result is that this is equal to, with this simplified notation, this mu b will go away when you take a trace b. It is a complete orthonormal basis, but this part will survive, and the result is this particular combination. Mu, this will produce rho A with the outer product, and then the other half will produce mu dagger. So this is the CPTP map. The equation is not too complicated, it's rather straightforward. These are some matrices mu and mu dagger which obey this property for completeness. But otherwise they are arbitrary. They are arbitrary in the sense that I could have taken any unitary action and calculated whatever this object is. So it depends on the interaction between the two parts, but that is the result.
Could we have chosen something other than 0? Could we have chosen something other than 0?
You could have chosen any fixed states. The 0 was just a convenient label. Okay. But it was a fixed state, whatever it is. So you can take the dot product and call it here, instead of 0 be some other state, just a label. But it is fixed. And in the next lecture, I will describe the consequences of this statement, just like I described all kind of consequences of the Schmidt decomposition today. But the equation is rather simple. Remember that original, for pure states, we had the rule that rho looked like this, U rho U dagger. It just happens to be the situation where there is only one term in the summation, all related to the fact that only one eigenvalue is 1 for a pure state density matrix, all the other one are 0. So this is a generalization that instead of having only one term, I can have more terms. The unitary nature would say that U dagger U is equal to identity is kind of buried inside here. With mu dagger M, mu summed over mu will become identity. So instead of having one term, I can have multiple terms and retain the normalization. Okay. And this statement also includes the other half of the quantum dynamics, which this which is that it includes the definition of what happens in a measurement. Remember, the definition of measurement was, which is rho going to pi rho pi, where pi's were projection operators. And there were many terms depending on how many independent directions are there in the projection. That is also included in this definition. Because the projection operator had a property that if sum over all pi, sum over I, it gives identity, which is equivalent to this definition. So this is the advantage we gained by this generalization, that there were two separate things in the Hilbert space construction. There was a unitary evolution and there was measurement of the operator, which gives you some projection and some eigenstate. Those two axioms got combined into one. And that is this particular definition. You don't need to talk about this separately. And of course, why did it happen? Because what is a measurement? There is a system and there is an apparatus. And we took care of the apparatus by going to this bipartite system, the other half is the apparatus. So what happens with the measurement? Well, the apparatus does something, we don't have to give all the detailed stuff, but we know what happens to the system. It's going to produce some eigenvector and some eigenvalues, and that is buried inside this construction in a clever manner. So that is a extra power you gain by going to this generalized structure. Don't have to talk about evolution and measurement separately, they are part of the same story. And the other features which are there for any property of the density matrix, which are all kind of buried inside here. So if you look at this map, it is a Hermitian. It is a trace. Because this is a discrete map. Hermitian, well, you take a Hermitian conjugate, it comes back to the same thing. Trace preserving, while if you take a trace of it, this mu dagger mu equal to identity will allow you to do jugglery, you will get back the same trace. And on top of that, you can prove that it is positive as well. So the eigenvalue of the original matrix are positive, then this will also come out to be all positive eigenvalues. For that you have to write it for arbitrary states, but it has this nice property. And yeah, that is a generic prescription, and it has a name, so I should write that one down as well. It's called the Kraus representations, and in particular this mu, they are known as Kraus operators. Kraus is the name of the mathematician who did all this demonstration, and it's very useful in writing arbitrary quantum evolution. And as I mentioned before, if you want to take this and make this evolution infinitesimal in time, you can convert it into a differential equation. It's an analog of converting this to Schrodinger equation. That can be done. That's not a problem. And yeah, there is yet another name, because there is a sum over operators. Sometimes it is called operator sum. These are all terminology which you might encounter in looking up in books. Instead of having one operator, you have multiple operators, so it's sometimes also called an operator sum representation. But this is a powerful and a general description of a quantum system which may or may not interact with the environment. So you don't have to worry about things getting exchanged between the system and the environment. This formalism is capable of describing them. So if you look at the real hardware or something like that and you want to model it, the best thing is to use this language to model the real hardware, because it has, whether you want it or not, some interaction with the environment. So yeah, that is as much as I want to say. And what are the consequences that we'll deal with next time? System interacts with the environment. What does this give you as a constraint on that framework? It is sometimes also called an open system analysis, where open means the environment is present. This thing, a pure state, is the closed system. Okay. Fine, I will stop here.